Hello everyone, in this lecture we will discuss crystal binding and elastic constant. Now in this chapter we are concerned about what holds a crystal together. Now the attractive electrostatic interaction between negative charges of the electrons and positive charges of the nuclei is completely responsible for the cohesion of solids. Now magnetic forces have only weak effect and gravitational forces are negligible. Now let's define the cohesive energy. A cohesive energy of a crystal is defined as the energy that must be added to the crystal to separate its components into neutral atoms at rest at infinite separation with the same electronic configurations. Now, lattice energy is defined as the energy that must be added to the crystal to separate its component ions into free ions. So, lattice energy is related with ions. Now, let's start with crystals of inert gases. Crystals of inert gases are transparent insulators weakly bounded with low melting temperature. The atoms have very high ionization energy and the outermost electron shells of the atoms are completely filled. In addition, the distribution of electron charge in the free atom is spherically symmetric. The crystal of inert gases, atoms pack together as close as possible. Now let's write them down. Crystals of inert gases are all cubic closed pack structure like FCC except helium-3 and helium-4. All have cubic closed packed structure except helium-3 and helium-4. Now the big question is what holds inert gas crystals together. So the electron distribution in the crystal is not significantly distorted from the electron distribution around the free atom because not much energy is available to distort the free atom charge distribution. Now part of this distortion gives the van der Waals interaction. So let's start with van der Waals interaction. To understand this model, let's consider that we have two identical inert gas atoms at separation are large in comparison with the radii of the atoms. In other words, two identical linear harmonic oscillators 1 and 2 separated by distance r. Now each oscillator have a charge plus or minus e with separations x1 and x2 as in this one here. Now as in this model here we have here two oscillators with charges plus or minus e and separations x1 and x2, and r in this case is much greater than x1 and x2. Now the particles oscillates along the x-axis. In this case here, the Hamiltonian of the unperturbed system is H0, which consists of kinetic energy and elastic potential energy. So the Hamiltonian in this case it's equal to P1 square over 2m plus half C x1 square plus P2 square over 2m plus half C x2 square. In such a way, C here is the force constant which equal to C equal to m omega naught square. Now another interaction we have here, it's Coulomb's interaction, and let's name it H1. So the Hamiltonian H1 equal to E square over R, which is the interaction between this one and this one here. It's E square over R plus E square over R plus x1 minus x2, which is the interaction between this one here and this one here, minus E square over R plus x1, which is in this case here is the interaction between this one and this one here, minus E square over R minus x2, and this one is the interaction between this one and this one. So the total Hamiltonian in this case, it's equal to H naught plus H1. Now before going further in this one, let's have an approximation. Since R is much greater than x1 and x2, in this case here, let's expand the Coulomb's interaction Hamiltonian, this one, and use the series 1 over 1 minus x to the power p equal to 1 minus x plus x squared minus x cubed plus and so on. Now this series can be used only if x in this one here it's very small. So let's apply this one here on the Hamiltonian H1. So let's start with this part here. So E squared divided by R plus x1 minus x2, p in this case it's equal to 1. Now if we take R as a common factor from this one, this will be equal to E squared over R 1 plus x1 minus x2 over R. And this is x, by the way, in this series. This equal to minus 1 plus x1 minus x2 over R minus x1 minus x2 over R square plus x1 x2 over R cube, and so on. Now let's expand E squared R plus x1, this one here, and this equal to E squared, again same rule, just have R as a common factor, 1 plus x1 over R. And remember, R is very large here, x is very small, so this amount here is very small, so this series is applicable here. Is equal to minus 1 plus x1 over R minus x1 over R square plus x1 over R cube, and so on. Let's continue here. Add this expansion for this one here. So E squared over R minus x2, in this case it's equal to E squared over R times 1 minus x2 over R, which equal to 1 minus x2 over r plus x2 over r square minus x2 over r cube, and the higher orders. And the last one is this one here, right here. So a square over r equal to, just leave it as is, it's just 1 here. Now remember, all these equations are multiplied by a square over r, a square over r, a square over r, and last one here, it's a square over r. Now remember, h1 equal to a square over r plus a square over r plus x1 minus x2 minus a square over r plus x1 minus a square over r minus x2. Now when we add all these approximations, this one here, and this one here, this one, and this one, and this one, and this one, in the same order of this Hamiltonian here, and ignore the higher order, in this case here, h1 equal to, it's approximated, minus 2 a square x1 x2 over r cube. Now the total Hamiltonian with the approximate form, this one here, can be diagonalized by the normal mode transformation. So XS stands for symmetric, equal to 1 over square root of 2 x1 plus x2, and X antisymmetric equal to 1 over square root of 2 x1 minus x2. Same thing for P symmetric, equal to 1 over square root of 2 p1 plus p2, and P for antisymmetric equal to 1 over square root of 2 p1 minus p2. Now if we solve these transformation modes and get x1 from this one here equal to 1 over square root of 2 x symmetric plus x antisymmetric, and x2 equal to 1 over square root of 2 x symmetric minus x antisymmetric. Same thing for p1 equal to 1 over square root of 2 p symmetric plus p antisymmetric, and p2 equal to 1 over square root of 2 p symmetric minus p antisymmetric. Now if we substitute these normal transformation modes in the unperturbed Hamiltonian H naught, it's just reminded, equal to p1 square over 2m plus half c x1 square plus p2 square over 2m plus half c x2 square. Now if we substitute p1, p2, x1, x2 in this Hamiltonian here, we will get H naught equal 1 over 2m half p symmetric square plus p antisymmetric square plus 2 ps pa plus half p symmetric square plus p antisymmetric square minus 2 ps pa. This is p1 square and this p2 square plus half C x symmetric plus x antisymmetric square over square root of 2 plus x symmetric minus x antisymmetric over square root of 2 square. Now the Hamiltonian, simplify this one here, 1 over 2m half ps square pa square plus 2ps pa plus ps square pa square minus 2 ps pa plus half c half xs square xa square plus 2xs xa plus xs square x antisymmetric square minus 2xs xa. In this case, this one cancel out with this, and this one cancel out with this. So the Hamiltonian in this case equal to, and this one here, 2 ps plus 2 pa, so they have cancel out as well. So 1 over 2m times ps square pa square plus half c x symmetric square plus x antisymmetric square, and h1 in this case, remember, equal to this one right here. This is h1 minus 2e square x1 x2 over r cube. Now if you substitute x1 and x2 with the normal transformation modes, we will get in this one here equal to minus, this is h1, equal to minus 2e square over r cube. Now 1 over square root of 2 x symmetric x antisymmetric times 1 over square root of 2 x symmetric minus x anti-symmetric. You simplify this one here, you will find h1 minus 2e square over r cube times 1 over 2 x symmetric square plus x anti-symmetric square. Or in other words, it's equal to e square minus over r cube x symmetric square plus x antisymmetric square. Now let's pull everything together. So h here, the total Hamiltonian, it's equal to h naught plus h1. In other words, 1 over 2m here times p symmetric square plus p antisymmetric square plus half c x symmetric square plus x antisymmetric square minus e square over r cube x symmetric square plus x antisymmetric square p symmetric square plus half c plus e square over r cube times x symmetric square. We just collected the symmetric together and the antisymmetric together in this one here, plus 1 over 2m p antisymmetric square plus half c minus e square over r cube times x anti symmetric square. And from this one here, we can see that we have two new frequencies, this one here and this one here. So omega in this case, it's equal to C plus or minus 2e square over r cube divided by m. And remember, omega naught, it's equal to square root of c over m. Now the plus here for symmetric and the minus here, it's for anti-symmetric. So omega symmetric, it's equal to c plus 2e square over r cube divided by m. And omega anti-symmetric, it's c minus 2e square over r cube over m. Now let's expand the frequency here using the series here, 1 plus or minus x to the power half equal to 1 plus or minus half x minus 1 over 8 x square. In this case here, omega plus, or in this case symmetric, equal to 1 plus half 2e square over cr cube minus 1 over 8 2e square over cr cube square, and so on. And omega minus equal to 1 minus half 2e square cr cube minus 1 over 8 2e square over cr cube square, and so on. And remember again, omega naught equal to c over m to the power half. Now the 0 point energy is half h bar omega, and omega in this case, it's equal to omega symmetric plus omega anti-symmetric, because the interaction is lowered from uncoupled value, which is in this case 2 times half h bar omega naught. And in this case here, the energy delta U equal to half h bar delta omega symmetric plus delta omega anti-symmetric. In other words, it's equal to minus h bar omega naught times 1 over 8 2e square over cr cube, or equal to minus a over r to the power 6. And this one here, this one right here, is the attractive interaction, which is also known as London interaction or the induced dipole-dipole interaction. And for identical atoms, the value of A is approximately equal to h bar omega naught alpha square. In such way, h bar omega naught is the energy of the strongest optical absorption line. Alpha in this case is the electronic polarizability. This one for identical atoms. Now let's discuss the repulsive interaction. Now, as the two atoms are brought together, their charge distribution gradually overlap, like this one here. So this is the, like this one here. Now when they brought together, their charge distribution will overlap. So this is the overlap here. At enough close separations, the overlap energy is repulsive, mostly because of the Pauli exclusion principle. Just a quick reminder for Pauli exclusion principle: two electrons cannot have all their quantum numbers equal. Now, assuming that we have atom A and atom B, in this case here, there is a high tendency for electrons from atom B to occupy in part states of atom A, which is already occupied by electrons of atom A, and vice versa. And Pauli principle prevents multiple occupancy. Now, for the repulsive interaction, we will not try to evaluate repulsive interaction, and experimental data of the inert gases can be fitted very well by the empirical repulsive potential, which is in this case here, it's equal to B over R to the power 12. In such a way, B is positive constant, here positive, and therefore the total potential, let's name it UR here, equal to, for epsilon, sigma over R to the power 12 minus sigma over R to the power 6, and this is called Lennard-Jones potential. Remember, this comes from the attractive, and this one is the repulsive interaction. In such a way, here, epsilon and sigma are new parameters with, for epsilon, sigma to the power 6 equal to A, and for epsilon, sigma to the power 12 is B. Now, to find the force between the two atoms, F here equal to minus du by dr. Sometimes the repulsive interaction can be written as lambda is exponential minus r over rho. This is another form of repulsive interaction. Now, by neglecting the kinetic energy of the inert gas atoms and sum over all pairs of atoms in the crystal, in this case here, U total here equal to half N for epsilon times summation. Again, we are summing over all pairs of atoms, sigma over Pij R to the power 12 minus summation sigma over Pij R to the power 6. This half here to avoid counting twice each pair of atoms. Pij R is the distance between reference atom I and any other atom J. For instance, the summation here for Pij to the power minus 12 for FCC structure, it's equal to 12.13188, and the summation Pij for the same structure, FCC structure, to the power minus 6, it's 14.45392. If we look for the equilibrium value R0, we have to derive the total energy with respect to R and equal to 0. So du total by dr equal to 0, in this case here, minus 2 and epsilon times 12, it's for FCC structure, 12.13, sigma to the power 12, R to the power 13, minus 6, 14.45, a sigma square over R to the power 7, and in this case here R0 over sigma equal to 1.09 for FCC structure. Now to calculate the cohesive energy of inert gas crystals at absolute zero, now let's use U total in this case here equal to 2n epsilon times 12.13 sigma over R to the power 12 minus 14.45 times sigma over R to the power 6. At equilibrium, when R equal to R naught, in this case, U total, after all, it's equal to, at R naught here, equal to minus 2.15 for an epsilon. Let's discuss ionic crystals. Ionic crystals are made up of positive and negative ions. This ionic bond results from electrostatic interaction of oppositely charged ions. The most common ionic crystal is sodium chloride, NaCl. Note, the electronic configurations of all ions of a simple ionic crystal correspond to closed electronic shell like inert gas atoms. Another example for ionic crystals is lithium fluoride. In lithium fluoride, the electronic configurations of neutral atoms are, so this is lithium, 1s2, 2s, and fluoride 1s2, 2s2, 2p5. As we can see here, outermost shell here is missing one electron, and the outermost shell, like in here, is having an extra electron. So in order for ionic crystals, this will accept one electron and this one will lose one electron. So the lithium ion, and in this case it's a plus because it lost one electron, 1s2. Now fluoride ion, in this case it accepts electron and it's minus, and it will be in this case 1s2, 2s2, 2p6. It's expected that the charge distribution on each ion in ionic crystals will have approximately a spherical symmetry. Now let's define electrostatic or Madelung energy. The van der Waals part of the attractive interaction in ionic crystals makes a relatively small contribution to the cohesive energy in ionic crystals of the order of 1 or 2%. Now the main contribution of the binding energy of ionic crystals is electrostatic, and it's called Madelung energy. Now if Uij is the interaction energy between ion I and ion J, let's define Ui, which includes all interactions involving the ion I. So Ui in this case is defined as summation over all interactions involving the ion I, it's named prime, J. Now the summation includes all ions except that I equal J. We suppose that Uij can be written as the sum of central field repulsive potential, and it can be written in the form Uij here in the form lambda exponential minus r over rho. In such a way, lambda and rho are empirical parameters, and the column potential is plus or minus q square over r. Now this is repulsive interaction, and this one column's potential interaction. and therefore Uij here equal to lambda exponential minus Rij over rho plus or minus Q square over Rij. And by the way, this is in CGS system. Don't forget that the plus sign is taken for like charges. So this like charges. And the minus sign is taken for unlike charges. And another quick reminder, the repulsive term describes the fact that each ion resists overlap with the electron distribution of neighboring atoms. So we treat lambda and rho as constant and can be determined from the observed values of the lattice constant and compressibility. We also neglect surface effect and write the total lattice energy, U total, here of the crystal composed of n molecules or 2n ions. U total of a crystal composed of n molecules or 2n ions. Therefore, U total equal to n Ui. Now we use n here rather than 2n because we must count each pair of interactions only once, or each bond only once as well. Once again, the total lattice energy is defined as the energy required to separate the crystal into individual ions at an infinite distance apart. Again, it's convenient to introduce Pij factor, Pij quantity, in such a way Rij equal to Pij R. R here is the nearest neighbor. If we include the repulsive interaction only among the nearest neighbors, so we will have in CGS system here Uij equal lambda exponential minus R over rho minus Q square over R, and plus or minus when Pij Q square over R. This happens for nearest neighbors. And this happens otherwise. Remember, we take this repulsive part only for nearest neighbors and minus because of the unlike charges. It's ions, positive, negative, positive, negative. So the nearest neighbor has to be in the opposite sign, so it should be minus. So other than the nearest neighbors, the only interaction we have is Coulomb's interaction, and it could be positive or negative and depends on the position here of the atom. U total in this case here can be written as n Ui or equal to n times z lambda e2 minus R over rho minus alpha Q square over R, where Z here is the number of the nearest neighbors of any ions. Let's define it here. And alpha is the Madelung constant, which is equal to summation plus or minus divided by position Pij under J. Remember, the sum should include all nearest neighbor contributions, which is just Z, and we already discussed plus and minus signs. So the value of the Madelung constant is the central importance in the theory of the ionic crystals. Now at the equilibrium separation, du total by dr equal to 0, this is for equilibrium, in such a way n dui over dr equal to minus n z lambda over rho exponential minus r over rho plus n alpha q square over r square, all equal to 0 because we are looking for the equilibrium position here, and r naught exponential minus r naught over rho equal to rho alpha q square over z lambda. And from this equation we can determine the r naught in this one here. You substitute back in u total equal to minus n alpha q square over r naught times 1 minus rho over r naught. And this one here is the total energy of crystal of two anions at their equilibrium separation r naught. So in r here equal to r naught. And this term right here is called Madelung energy. So minus n alpha q square over r naught is Madelung energy. And alpha is the Madelung constant. And alpha equal to summation over j plus or minus pi j, and this is Madelung constant as we mentioned before. Now for stable crystal, it's very important that alpha is positive. So alpha is positive for stable crystal. Example, let's calculate the Madelung constant for infinite line of ions of alternating sign plus or minus. So if we have here plus or minus ions like this one here with distance here between positive and negative ions is r. Now we would like to calculate the Madelung constant for this case. Now let's take the reference point and let's take it the negative ion. The reason why we take the negative ion is that the plus sign will apply to positive ion and the minus sign will apply for to negative ion. Otherwise, if we take the positive ion as a reference, in this case the negative will apply for the positive and the positive will apply for negative, and so confusing. So let's take the reference here is the negative sign. Remember, Madelung constant equal to summation over all ions plus or minus Pij over R, this one here. So let's do this. Alpha over R equal to 2 times 1 over R minus 1 over 2R plus 1 over 3R minus 1 over 4R, etc. The 2 here, because we are counting ions to the right and to the left of the reference point. And alpha equal to 2 times 1 minus half plus 1 over 3 minus 1 over 4 plus and so on. If we use this series len 1 plus x here, it's equal to x minus x squared over 2 plus x cubed over 3 minus x4 over 4 and so on. And we compare this series here with this series here with the result here, we will find that x in this case it's equal to 1, so all this one here equal to len 2, so alpha equal to 2 len 2. In other words, the Madelung constant for one-dimensional chain is equal to 2 len 2. It's good to mention that in 3 dimensions, the situation is very complicated and we cannot do this manually. Now let's move to another type of crystals. It's covalent crystals. In covalent crystals, there are strong bonds and usually formed from 2 electrons, and the electrons forming the bond tend to be partially localized in the region between the 2 atoms joined by the bond, and the spin of the 2 electrons in the bond are anti-parallel, and they all have low filling space, which around 0.34 comparing to 0.74 for closed back structure. Pay attention here that the Pauli principle gives a strong repulsive interaction between atoms with filled shells, but if the shells are not filled, electron overlap can be accomplished without excitation of electrons to high energy states, and the bond will be shorter. Now let's discuss metallic crystals. Now metallic bonds are characterized by high electrical conductivity, and large number of electrons in a metal are free to move, which usually 1 or 2 per atom. Those electrons are called conduction electrons. Just to mention that metals tend to crystallize in relatively close packed structures like HCP, FCC, and BCC, and some other closely related structures, and they are not loosely packed structures like diamond. Now let's discuss hydrogen bonds. Now, because a neutral hydrogen has only 1 electron, it should form a covalent bond with only 1 other atom. Now, sometimes under certain conditions, an atom of hydrogen is attracted by rather strong forces to 2 atoms. Therefore, they form, in this case, a hydrogen bond. An example for this, it's water molecule, it's H2O. Now let's analyze the elastic strains. To analyze elastic strains, we will use the basic ideas of Hooke's law and Newton's second law. Now, Hooke's law states that in an elastic solid, the strain is directly proportional to the stress. And remember, this law applies only to small strains. Now, in other words, for nonlinear region, when the strain is so large, the Hooke's law is no longer satisfied. Strain is specified by the components EXX, EYY, EZZ, EXY, EYZ, and EZX. And those are strain components. Again, we are dealing with infinitesimal strain only. Imagine that we have 3 orthogonal vectors x hat, y hat and z hat, this x hat and z hat. Now after small deformation of that solid, so the new axes will be after small deformation x prime, y prime and z prime, and those new axes can be written as x prime equal to 1 plus epsilon xx x hat plus epsilon yx y hat plus epsilon xz z hat, and the new axis on the y-axis or y prime equal to epsilon yx x hat plus 1 plus epsilon yy y hat plus epsilon yz z hat, and z prime equal to epsilon zx x hat plus epsilon zy y hat plus 1 plus epsilon z hat. Now coefficient epsilon alpha beta is defined as the deformation, and it's dimensionless with values much less than 1. So epsilon alpha beta is much less than 1 if the strain is small. Notice that the original axes x hat, y hat, z hat were of unit length, but the new axes x prime, y prime, z prime will not necessarily to be of unit length. To prove this one here, let's find x prime dot x prime. In this case, it's equal to, use this one here, equal to 1 plus to epsilon xx plus epsilon xx square plus epsilon xy square plus epsilon xz square, and notice here it's not of unit length dimension. Now x prime is approximately equal to 1 plus epsilon xx and so on here, and the fractional changes of length of the x hat, y hat, z hat are epsilon xx, epsilon yy, epsilon zz to the first order. Let's discuss the effect of deformation on an atom originally located at r equal to x hat, xx hat plus yy hat plus zz hat. Now assuming that the deformation is uniform, then after deformation position r will be at the position r prime equal to xx prime yy prime plus zz prime. This one here, right here, the original position, and this one right here is the after deformation. Now the displacement r equal to r prime minus r, or equal to x prime minus x hat plus y prime minus y hat plus z prime minus z hat, and this is the displacement. And by using these equations here, R will be equal to x epsilon xx plus y epsilon yx plus z epsilon zx all x hat plus x epsilon xy plus y epsilon yy plus z epsilon zy, and in terms multiplied by y hat plus x epsilon xx plus y epsilon yz plus z epsilon zz times z hat. In a more general form, let's introduce u, v, and w. In this case here, r equal to u of r x hat plus v of r y hat plus omega of r z hat. And remember, if the deformation is non-uniform, we have to relate u, v, w to the local strains. Now, by comparing this one here and this one here and use Taylor series expansion, we will find that x epsilon xx equal to approximately x partial u partial x and y epsilon yx equal to y partial u partial y, etc. It's usual to work with coefficient E alpha beta rather than using epsilon alpha beta. So E alpha beta instead of using epsilon alpha beta, and from now on we will use E alpha beta. So EXX, EYY, EZZ. Now EXX equivalent to epsilon XX, which equal to u partial x, and EYY, which equivalent to epsilon YY, which equal to partial v partial y, and EZZ equivalent to epsilon ZZ, or equal to partial omega partial z. Now the other strain components, the mixed terms EXY, EYZ, EZX, are defined in terms of the changing in the angle between the axes. Now, with the aid of the equations we mentioned before, this one here, right, one here, this one here, we will find that EXY equivalent to x prime dot y prime, or equal to epsilon yx plus epsilon xy, or partial u partial y plus partial v partial x. Now EYZ, it's equivalent to y prime dot z prime, or equal to epsilon zy plus epsilon yz, or equal to partial v partial z plus partial omega partial y, and EZX equal to z prime dot x prime, or equivalent to epsilon zx plus epsilon x z, or partial u partial z plus partial omega partial x. Since epsilon is much less than 1, we can ignore the higher order or epsilon square and so on. And from this, the 6-dimensionless coefficients E alpha beta or E beta alpha completely defines the strain. Now let's define dilation. Now the fractional change of volume associated with deformation is called dilation. In simple words, the change in volume which is related to the deformation is called dilation. So the unit cube of edges x hat, y hat, z hat has a volume after deformation v prime equal to x prime y prime cross z prime. X prime dot y prime cross z prime, it's equal to 1 plus epsilon xx epsilon xy epsilon xz epsilon yx 1 plus epsilon yy epsilon yz epsilon zx epsilon zy 1 plus epsilon zz. Solving this determinant, we'll find that 1 plus e xx plus e yy plus e z. Now the fractional change or dilation, it's equal to the new volume after deformation minus the original volume divided by the original volume, which is approximately equal to exx. Remember, approximately because we ignore the higher orders. So exx plus eyy plus ezz. So far, we discussed the strain components. Now let's define stress components. Now, the force acting on a unit area in solids is defined as stress. In such a way, 9 stress components we will have here. So we'll have x, xy, x, z, y, x, y, z, z, x, z, y, z, z. And remember, the capital letter indicates the direction of the force. So direction of force, and the subscript indicates the normal to the plane to which the force is applied. Normal to the plane to which the force is applied. As we can see here, we have 9 stress components, like in this one here. Now, as we can see here, x, y is the force applied in the x direction to a unit area of plane whose normal lies in the y direction. And yx is the force, same definition with small changes, applied in the y direction to unit area of plane whose normal lies in the x direction. So this is xy and this is yx and this is xy and this is yx. As we can see here, the sum of the forces in the x direction is 0 and the sum of the forces in the y direction is also 0. So the total force vanishes and the total torque about the origin is also 0 if yx here equal to xy. And from this one here, the 9 components of the stress becomes 6 components because yz for the same reason equal to zy and zx equal to xz and xy equal to yx. Therefore, the 9 components becomes this: x, y, z, y, z, x, and x, y. Remember here, the stress components have the dimensions of force per unit area or energy per unit volume, but strain components are ratios of lengths, which is dimensionless. Now let's relate the stress and strain components. By using Hooke's law, the relation between the stress and strain can be summarized as in this: Exx equal to S11 xx plus S12 yy and so on until we have the 6 strain components Exy, which is related to 6 stress components Xy. In such a way, S11 here, S12 and so on are called elastic compliance constants, and C11, C12 and C13 and so on are called elastic stiffness constants. Now remember, the S's have the dimensions of area per unit force. So S here, dimensionality of S is area per force or volume per energy. But the C have the dimensions of force per unit area or energy per unit volume. So C is force per unit area or energy per volume. And this one here, stress is written in terms of strain. Now the elastic energy density, U in this case here, is a quadratic function of the strain and is written as half summation over lambda equal to 1 to 6 and mu equal to 1 to 6 C lambda mu E lambda E mu. And to simplify things, let's just use the indices 1 through 6. So 1 equivalent to XX, 2 equivalent to YY, 3 equivalent to ZZ, 4 equivalent to YZ, 5 equivalent to ZX, and 6 equivalent to XY. Now the stress components are found from the derivative of U as we defined before, and in this case XX equal to du by dExx, which is equivalent to partial U partial E1 or C11, this one here, E1, remember XX equivalent to 1, plus half summation C1 beta plus C beta 1, this one here, E2 beta, and beta from 2 to 6. Note here that the only combination which is half C alpha beta plus C beta alpha enters the stress strain relations, which leads to C alpha beta equal to half C alpha beta plus C beta alpha or equal to C beta alpha. In other words, C alpha beta equal to C beta alpha. Because of this condition here, the 36 components in this one here, the 36 components, because C alpha beta equal to C beta alpha. Now, excluding the C alpha alpha here, which is in the diagonal, this one here, C alpha beta, like C1 2, it's equal to C2 1, 1 3 equal to 3 1, and so on. So the 15 terms here, 15, is the imaged with those 15. So instead of having 36 terms, we will have 15 term plus 6 in the diagonal. So the 36 terms, or the 36 elastic stiffness constants, are reduced to 21. So 36 elastic stiffness reduced to 21 elastic stiffness term. Now, as a special case, let's consider elastic stiffness constants for cubic crystals. The reason we use cubic, it's a highly symmetric system, and therefore, rather than having 36 or even 21 elastic stiffness terms, let's see how much elastic stiffness we will get. U here equal to half C11 EXX square EYY square EZZ square plus half C44 EYZ square plus EZX square plus EXY square plus C12 EYY EZZ plus EZZ EXX plus EXX EYY. And remember, there's no other quadratic terms occur, which means EXX EXY and EYZ EZX and EXX EYZ. Those terms will never occur for cubic system. As we discussed earlier, the minimum symmetry requirement for a cubic structure is the existence of 4 3-fold rotations. In other words, the effect of rotation of 2 pi over 3 about these 4 axes is to interchange the x, y, z axis according to the following. X rotated around the y, rotated around the z, x, and minus x, z, y, minus x, x, z, minus y, x, minus x, y, z, minus x. This is 4 3-fold rotation. For instance, EXX square plus EYY square plus EZZ square under the first of these schemes becomes EYY square plus EZZ square EXX square. As we can see, it's not changing. And similarly, for the other terms in the parentheses in this equation here, this U here, it's invariant under the operations considered. Now we want to verify the numerical factors in this energy here, this U here, with the aid of this equation here, this one here. Let's just write it down. This one right here. I just wrote them down, this one and this one right here. Partial U partial EXX is actually equal to XX, which equal to, so if we derive U, this U with respect to EXX here, so this factor will be 0, this one will be 0, this is 0, this one 0, this one 0, and this whole thing is equal to 0 except this one here. So it's equal to C11, this one here, 2 with the half EX x plus C12, this one right here, EYY plus EZZ. If we compare this one here with the matrix stress-strain relation, this one right here, you will see by comparing factor by factor. Now C11, it's already in here, and C12 is related with EYY and EZZ. This one here, it's EZZ, it's related with 1,3, but this one it's C12, so C12 is actually equal to C13. Now C14, there is no YZ in this equation here, so C14 equal to 0, and C15 right here, again no ZX, so C15 again equal to 0, and C16 no XY, so it's equal to, again it's equal to 0. Same procedure if we try to find partial U partial EXY, which is in this case XY. Remember, capital letter, this one here is the force direction, and here it's the perpendicular to the area. This one here, if we go to this equation right here and we would like to derive U with respect to EXY, now this one here is equal to 0, this one here is equal to 0, and this one here equal to 0. So in this case there is no C11 in this one here, but in XY, this one here, you will find it's equal to C44 EXY, and no other terms we'll find this here or even in this. Now by comparing this one here with XY, this is XY right here, now you will find that there is no XX in this here, so C61 equal to 0, and this is YY, there is no YY in this one here. We compare this one with this one here, C62 equal to 0 as well, C63 again it's equal to 0, 64 equal to 0, and 65 equal to 0, and the only one we have here is 66, and it's related with EXY, and this is C44. In this case, C44 is actually equal to C66. Now by following the same procedure, you will find that the 36 terms, which reduced to 21 because of the symmetry, now the 21 terms reduced again to 3 terms, only 3, C12, C11, and C44. This is for cubic system. So for cubic system here, crystal, the 21 terms reduced to C11, C12, and C44. Again, for cubic crystals, the stiffness and compliance constants are related by this. C14 is actually equal to 1 over S44, and C11 minus C12 is equal to S11 minus S12 to the power minus 1, and C11 plus 2C12 is actually equal to S11 plus 2S12 to the power minus 1. And you actually can find these by calculating the inverse of the matrix we mentioned before. Now let's calculate bulk modulus and compressibility. Assume that we have a uniform dilation, which means AXX equal to AYY, which equal to AZZ. And because of this equality, the dilation will be 1 over 3 delta. Now, the U in this case is equal to 1 over 6 C11 plus 2 C12 times delta square. Again, this is U, I just wrote it down here. Now, if EXX equal to EYY, which equal to EZZ, and equal to 1 over 3 delta, now let's just substitute instead of this one here, and this one here, this one, and this one, and this one, and no need for this one here, and this. And if we substitute with this and this one here, you will find U equal to 1 over 6 C11 plus 2 C12 delta square. Now the bulk modulus is equal to U equal 1 over 2 B delta square. And remember, this definition is equivalent to the definition minus V dP by dV. And for cubic systems, B equal to 2U divided by delta square. In other words, B equal to 1 over 3 C11 plus 2 C12. We just substitute U, this one here, back in this one, and we got here the bulk modulus. The compressibility, K here, is actually defined as 1 over B. So once we calculated the bulk modulus, we can find the compressibility directly in this case. So K here equal to 3 divided by C11 plus 2 C12. Now let's find elastic waves in cubic crystals. Again, we used here Hooke's law and Newton's second law. And remember, Newton's second law is sum of all forces equal to ma, and a in this case is the second derivative of the displacement with respect to time. So Newton's second law, it's equal to rho, and we use here CGS. So instead of mass, we use here rho partial 2U partial T square. It's equal to partial x partial x plus, remember the force is related with the energy, partial x y partial y plus partial x z partial z. Now rho here is the density. Now this is second order differential equation, and if we substitute instead of x and y and z, you will find that rho partial 2u partial t square equal to C11 partial exx partial x plus C12 partial EYY partial x plus partial EZZ partial x. And remember, xx in this case, we calculated this one before with the aid of the matrix for cubic crystals. This one right here. Let's just go back here. This one here. So here is the relation between x and EX and EY and EZZ and so on. One more thing to mention here, that x, y, z directions are parallel to the cube edge. In this case here, let's simplify this one here. Partial 2u partial t square equal to c11 partial 2u partial x square plus c44 partial 2u partial y square plus partial 2u partial z square plus c12 plus c44 times partial 2v partial x partial y plus partial 2 omega partial x partial z. And this is actually the equation of motion. In such a way, u, v, and w are the components of the displacement. Now the other equations, rho partial 2 v partial t square equal to c11 partial 2 v. We actually followed the same procedure, partial y square plus c44 partial 2 v partial x square plus partial 2 v partial z square plus c12 plus c44 partial 2 u partial x partial y plus partial 2 omega partial y partial z, and the other one for the omega direction, rho partial 2 omega partial t square equal to c11 partial 2 omega partial z square plus c44 times partial 2 omega partial x square plus partial 2 omega partial y square plus c12 plus c44 partial 2 u partial x partial z plus partial 2 v partial y partial z. And again, these are the equations of motion. Now let's consider this case here. A wave is propagating in the x direction and its displacement in the x direction as well. In this case here, since the displacement in the x direction, we should use this equation right here. And this is second order differential equation. The solution will be something like this: u equal to u naught exponential I kx minus omega t. This is time dependent solution, and this is the propagation along the x direction for the wave. Now this is the solution. What we need to do here is applying this equation here back in this one right here, and you will find that omega square rho equal to c11 k square. We just apply this equation and this equation directly. You will find that it's equal to omega square rho c11 k square, and the velocity is actually equal to omega over k, so v equal to nu lambda and equal to omega over k, which equal to c11 over rho to the power half. And this is actually a longitudinal wave because its displacement and propagation are in the same direction. Now let's consider another case when we have a transverse or shear wave with wave vector along the x cube edge and with the particle displacement in the y direction. So we have here the particle displacement in the y direction, so we should use this equation right here. It's v. Now v in this case, again the same as this one here, v naught exponential I k. Now its propagation in the x direction, it's kx minus time dependent solution right here. Now when we substitute this one here in the second equation of motion, this one here, you will get omega square rho equal to C44 k square. Again, this is because of the propagation, it's in the x direction, and this is the displacement in the y direction. So propagation in x direction and displacement y direction. So omega square rho equal to C44 k square, and in this case here Vs, velocity or the speed, equal to C44 divided by rho and all in half. And again, this is a transverse wave, it's not longitudinal, because the displacement in direction and the propagation of the wave in another direction perpendicular to the displacement direction. Let's consider this case here. A wave propagates in the xy plane and the particle displacement, it's in the xy plane. So in this case here, we should have two solutions. It's u equal to u naught exponential I. It propagates in the xy plane. We should write kxx plus kyy minus omega t. This is the solution for the displacement u. And the other solution v, in this case here, it's v naught exponential I. Again, it propagates in the x and y, so kxx plus kyy minus omega t. Now when we substitute these two solutions in equation 1 and 2, this one here, equations of motion, this one, this is 1 and this is 2, when we substitute them back, you will get in this one here omega square rho u equal to C11 kx square plus C44 ky square all times u plus C12 plus C44 kx ky v, and the other solution will be omega square rho v equal to C11 ky square plus C44 kx square all times v plus C12 plus C44 kx ky u. Assuming that kx is equal to ky, which equal to k over square root of 2, because the wave is actually 1, 1, 0. By rearranging these two equations in a determinant, you will see that minus omega square rho plus half C11 plus C44 like this, k square half C12 plus C44 k square half C12 C44 k square and minus omega square rho plus half C11 plus C44 k square. This determinant equal to 0. Now to solve this one here, by just quick looking to this equation here, you will see that this factor is exactly the same as this one here, and this one is exactly the same as this one here. So the solution for this 2 by 2 determinant is when we multiply this by this and minus this by this equal to 0. So this with this is actually equal to this with this. So the square of this part here, just write it down, minus omega square rho plus half C11 plus C44 k square is actually equal to this one here, half C12 plus C44 k square all square. Now, by taking the root for these two equations, you will see that minus omega square rho plus half C11 C44 k square is actually equal to plus or minus half C12 plus C44 k square. Now if we take the plus sign, the positive one, this one here, you will see that minus omega square rho plus half C11 plus C44 k square, when you move this one to the other side, minus half C12 plus C44 k square. This is actually equal to 0, and this one will cancel out with this one here, and you will get minus omega square rho plus half C11 minus C12 times k square, and from this one here you will find omega square rho is actually equal to 0, this one here. When you move it to the other side, it's equal to half C11 minus C12 times k square, and this is one of the solution we have. Now for the negative solution, this one here, this one, you will find that minus omega square rho plus half C11 plus C44 k square, actually it's minus, when you move it to this side here it will be positive, plus half C12 plus C44 k square equal to 0. Rearrange this one here, you will find omega square rho equal to half C11 plus C12 plus 2C44 times k square, and this is actually the other solution. Let's write them in a separate sheet here. Now since we have here two solutions, this one here, let's name it 1 and 2. One of these solutions is longitudinal wave and the other one is transverse wave. Now to see which is which, let's have this test. Now if we apply this one here, this solution, the first one here, in one of these two equations, those two equations, let's apply it in this one here. Let's move it in the other part. If we substitute, let's say, the solution number 1 in one of these two equations, and we got u equal to, in this case, v, for this case, this solution will be longitudinal, otherwise it will be transverse. Let's test that one and see. If we substitute this in the first one here, you will see that omega square rho is equal to half C11 minus C12 k square times u, if you apply this in the first one here, equal to C11 kx square plus C44 ky square times u plus C12 plus C44 kx ky v. If we move this part right here, from this one to this one here, you will find that minus C12 plus C44 u equal to C12 plus C44 v. And from this here, u, it's actually equal to minus v, which means the first solution, this one right here, is transverse solution, transverse wave. Now, if we substitute the other one, half C11 plus C12 plus 2C44 k square u is equal to half C11 plus C44 k square u plus half C12 plus C44 k square v. By rearranging this equation here, you will find that u actually it's equal to v, and this is longitudinal wave. So this one here is longitudinal solution wave here. Now, to summarize the cases that we might face is when, assuming that this is XYZ, this one here, for the case 1, 0, 0, now the wave propagates in the x direction, this one here. We have actually two possibilities. Now, this one here, longitudinal, if it propagates in the x direction and the displacement in the x, and two transverse, this one transverse and this one is transverse, the longitudinal solution is related with C11, but the transverse solution is related with C44. As another case we might face is this one here, and the wave propagates in the 1, 1, 0, like the one we just solved a few minutes ago, is when the wave propagates between x and y. We have here longitudinal wave, this is k, in this direction, and we are actually having two transverse, this is T1 and this is T2. And remember, transverse are perpendicular to longitudinal and perpendicular to each other as well. So the longitudinal solution, we just saw that a few minutes ago, half related with half C11 plus C12 plus 2 C44, and the transverse 1 is related with half C11 minus C12, and transverse 2 is related with C44. And another case that we might face is when the wave propagates in the 1, 1, 1 direction. In this case here, this is the L longitudinal wave, and this is the propagation K here, L, and we're actually having two transverse, one in this direction and one in this direction, and in this case the longitudinal in this case is related with 1/3 C11 plus 2 C12 plus 4 C44, and transverse, we're actually having one transverse because this transverse is the same as this one here, and it's related with 1/3 C11 minus C12 plus C44. That's it. Thank you for watching.